Good afternoon. This video is about series. We're going to take a look at what a series is in general, and then we're going to look at two types of series. One is called an arithmetic series, and the other one is called a geometric series. So what I want to do is motivate the lesson with an exploration here that you see on the screen, and it's called Finding the Sum of an Infinite Sequence. And it says, consider the following square below with side length 1. Half of the square is shaded, then half of the remaining rectangle is shaded and is added to the previous area of shaded area. Suppose that this process is continued for an infinite amount of area, okay? And part 1 wants us to determine the area of the following regions. So we have 1 rectangle shaded, then we go to 2 rectangles shaded, then 3 rectangles shaded, and 4 rectangles shaded. So we want to determine the area, okay, if 1 rectangle is shaded. So based off what you see here, the area of that would be 1/2. So I'm going to put 1/2 here. And then for 2 rectangles shaded, that's going to be 1/2 plus 1/4. And that's going to give you 7/8, I believe. Just want to double check and make sure I'm correct. I'm sorry, that's not 7/8. I spoke, it's 3/4. Okay. Now for 3 rectangles shaded, that's 1/2 plus 1/4 plus 1/8. Because we're shading. Okay, so that's 7/8. And then for 4 rectangles shaded, it's 1/2 plus 1/4 plus 1/8 plus 1/16. That equals 15/16. Okay. All right. So part 2 says determine a formula for the area for n rectangles shaded. So if you notice the pattern here, okay, we have 1/2, then we add 1/4 to that, then we add 1/8 to that, and then we add 1/16 to that. And that's going to keep going. And if you notice, your denominators are powers of 2. And so because they're powers of 2, we have 1/2 to the power of n. So that will be the formula for the area of n rectangles shaded. And then part 3 says, does the total shaded area for the infinite amount of rectangles exist? Explain your reason. And so what's happening here is we're always adding half of the area that we're getting to the previous. So we're going to keep adding that. And what's going to happen is the answer will become yes. And so what's happening here is we're going to keep adding, and adding. And what's going to happen is we're going to actually get to, a finite area. Okay, so what's happening here is we started with a whole square. So we started with the whole square, and then we kept adding and adding 1/2 each time. Okay, so the answer to this question would be yes. So each time we add area, we add a smaller amount of area. And so as you can tell, this is a pattern. And so what's happening here? So we're adding something, okay? We keep adding something that follows a general pattern. So the question is, how do you deal with how you deal with expressions where we're adding an infinite amount of something? Okay. Well, first we need to talk about what does it mean to add something together an infinite amount of time. Okay. And that's going to lead to something called partial sums. Okay. And so the definition of sigma notation, which is a partial sum, is given by this symbol here. The Greek letter symbol looks like a little E. And so you have certain things added here and subtracted. Okay. You have things that are going to be added together. You have the summation sign. And then down here is called the index of the summation. And then this is called the starting point. Okay. And this is the element, they call it, or the sequence, okay, of the terms we're adding up. And this is the number we stop at. Okay. So it's understanding notation. Okay. Now we get to series, the main idea of this topic. So series and partial sums. So the bottom part of the series tells us what to start with. In this case, we start with k equals 1. This tells us to add, okay? And this tells us where to end. And this tells us what to add. We're adding up all the terms of a sequence, okay? And when you keep doing that an infinite number of times, then we have something called an infinite series, where your top bound is infinite. And so now we have properties of sums, okay? And all this is telling us is if we add up a constant, that's the same as multiplying that constant so many times. Here, if we have a series that's multiplied by some constant multiple, okay, C, then that's the same as factoring the C out and then adding up all your terms, okay? Here, if you have two series, okay, if you have two sequences you need to add up together, that's the same as adding the terms of each sequence separately. And then for subtraction, the same thing. You're subtracting two sequences, and that's the same as subtracting the sequences of each by themselves. So now let's do some examples involving finding a sum. So we're asked to find the sum of the asked to find this partial sum here. This is the series from k equals 0 to 4 of k squared. So first, let me write out what this is going to look like. So plug in 0, plug in 1, plug in 2, 3, and 4. You're going to add those together. Okay, so you get 0 plus 1 plus 4 plus 9 plus 16. And when you do that, you get 30. So the sum is 30. Here they want us to find the sum from k equals 3 to k equals 5, 1 over k squared minus 3. Same thing. Three, 4, 5. So this will be 1/5. This will be 1/13. This will be 1 over 22. And then I'm going to add those together. I get 124 over 429. All right. And this is how you would find the sum of a series. All I did was I start at the bottom and I keep plugging in until I get to the top number, and then I add up all the terms. Okay, that's for both of these. So here's some practice problems you can try on your own using the same process that I did before. Now I want to motivate the next part of this lesson with this exploration, which is called developing a formula for a sum of an arithmetic sequence. And so this person over here you see on the right, his name is Carl F. Voss. Okay, so this problem was attributed by him. And what it says here is consider the problem of finding the sum of the integers from 1 to 100. So first part of this exploration wants us to write the expanded form of the series from k plus 1 to 100 if k. I believe that would be trivial. And so that would be 1 plus 2 plus 3 plus 4 96, 97, 97, 98, 99, 100. Okay, so that's the expanded form. And then part 2, they want us to write the expanded form of the same series, but in decreasing order. So that's 100 plus 99 plus 98 plus 97, and then 4, 3, 2, 1. And then it says use part 1 and part 2 to add the integers vertically. So we're going to add like this, part 1 and part 2. And what you're going to notice is that's going to give you 101 plus 101 plus 101 plus 101. An infinite number of times. Okay? You get 101. Okay? Part 4 says use the result from part 3 to find the sum of the first 100 integers. So what we actually did here is we added the numbers twice, right? Okay, so we found the sum of the first 100 integers. So that's actually going to be 101, okay, times 50. Okay, so, excuse me, 101 times 50. Or actually, no, it's not. It's 101 times 100. Excuse me. 10,100. So it's going to be 101 times 100. And that's 10,100. Okay, now it says use the result from part 4 to find the sum of the first n integers. So actually what we did was we added these 2 times. Okay, we added these 2 times. So what we want to do is take this here and divide it by 2, because technically we added it twice. So take 10,000 100, divide that by 2, you get 5,050. Okay. So this is very interesting because I want to actually go back to part 4 for a minute. And I want to show you something. So the 101, that's right here. Okay, yes, we actually did that. But if you notice, the 101 is actually this first term and this last term added together. Okay, so it's that number. And then we divided 100 by 2 because we added twice. So that's interesting. And that actually leads to a formula for finding a sum of an arithmetic sequence or series. Okay. And here it is here. This is the formula that will allow you to find the sum of so many terms. an arithmetic series. Okay. Now keep in mind that this is a formula for partial sums. Okay, so this is a formula for partial sum. Okay, so you can use this formula or you can use this formula there. And it depends on what situation you want to, it depends on the situation, of course, depending on what's given. Excuse me. So if you know the first and last term, and then that means you can use this one. So if you know the first term and the common difference, you can use this one. So either one will work. Okay, so now let's find, let's do some examples using the sum, right? Okay, so this one wanted us to compute the 120th partial sum of the arithmetic sequence 6, 12, 18, 24, 30. Okay, and so first thing I would want to do here is I would want to find the 120th term, okay, because it's not obvious here. So let's find the nth term first. Okay, looks like the common difference is 6. You add 6 each time, that's the common difference. So the common difference is 6, we know that. Common difference is 6, and the first term is 6. So the common difference is 6 and the first term is 6, right? And so we can actually use the formula, find term 120, and that is S120 equals 1/2. 1/2 times n, n over 2, times 2 times term times n minus 1 times d. Okay. All right, so we're going to plug in our, so the n we're looking for, n is 120. That's the number of terms we add. Okay, so 120, A1 is 6, 20, and common difference is 6 there. Okay. And then you can plug all of that into the calculator. You get 43,560 as the sum of the first 120. Okay. So again, depends on, and again, let's be reminded of the formula for the nth partial sum. So Sn equals n over 2, a1 plus an, or you can use Sn equals n over 2 times 2an, or a1 plus minus 1 times b. You use either one. All right. Here's another example. 30th partial sum of the arithmetic series, 78 plus 76, all the way down to 60. Okay. Well, again, your common difference, find that first. Looks like it's minus 2 each time. Okay, so common difference is -2. First term is 78, and n is 30. Okay, n is 30. All right, so Sn or S30 is 30 over 2. Actually, write my formula out. So that is 30, and then this is 78. This is 30, and this is -2. Okay, 30th term, 15. 2 times 78 is 156. and I get 1,560. That's the sum of the first 30 terms of the 30th partial sum. Okay? So if you understand both of those examples, we can continue on to something like this. It gets a little bit more interesting. Okay, so this is the series from n equals 51 to 100 of 7n. All right, so here we have to consider the fact that our first term is really 51. Okay, and our nth term is term 100. So we're going to have to be careful here. Okay, so A51. So A51, let's find that. So that's going to be 7 times 51. Okay, that's 357. And then A100 is 7 times 100, which is 700. Okay, so how many terms are there? There are actually 50 terms in here, 50 terms. And so the formula we want to use is S50, and that's n over 2. And then we're going to do A51 plus, we're going to add these two together. So how many terms in here? There are 50 terms, right? So put 50 in here for n, okay? This is going to be 357 plus 700. And so when you add those together, or when you simplify that, it gives you a sum of 26,425. All right, so that's how you find partial sums, arithmetic sequences. Now here's some practice problems for you to do using some of those same processes that I did before. Okay. All right, so let's continue on. Now we want to take a look at some applications of arithmetic sequences and series. So this is an auditorium that you see here on the right. And it says an auditorium contains 36 seats or rows. There are 15 seats in the first row, 18 seats in the second, 21 seats in the third, and so on and so forth. It says determine a formula for the number of seats in the nth row of the auditorium. Okay, so based on this, let's kind of go back and identify some stuff. Okay, so 36 seats or rows. I'll say that's n. Okay. 15 is A1, A2, A3. Okay, so they give us A1, A2, A3. So n is 36, A1 is 15, A2 is 18, and A3 is 21. So based on this, it follows a pattern, and it looks like it's adding 3 each time. So the common difference is 3. So B is 3. Now the A1 is 36. Okay, A1 is 36. All right, so AN, so let's write our formula. AN equals A1 plus N minus 1 times D, which is the formula. Okay, and so AN, the nth term of this sequence, is given as 15. And I put 36 initially, and that's supposed to be 15. So 15 plus 3 times n minus 1. That is the formula for the nth term. Okay. So if I wanted to know how many seats were in the, say, fourth row, I plug in 4 for n. That's going to give you 3 times 3, which is 9 plus 15 is 24. So 24, which follows the pattern even. All right, part 2 says determine the total number of seats in the auditorium. And so that will require us to find you can use one or both formulas. You can find the 36 term and then use that formula with the first term, or you know the fact that A1 is 15 and D is 3. You can use the other formula as well. Okay, so we're looking for the sum of 36 rows. That's what we're asked to do. So S36 equals 36 over 2. Put that there. 2 times something plus n minus 1 times something. Okay, so 36. Put here your A1, which is 15, 36. Common difference is 3. So put all of that in, and 2,430. Okay, so 2,430 seats are in this auditorium. All right, so here is another application involving arithmetic sequences. It says you're given a job offer with a starting salary of $36,800. Each year you're given a raise of $1,750. Okay. Part 1 says determine the formula for the annual salary after n years. And then part 2 says determine the total amount of money made during 6 years of employment. Okay. So if we go back and break this down, this is a starting salary. So this will be A1. And every year I'm given a raise of $1,750. So that would be the common difference, B. So again, using our formula, we have AN equals A1 plus N minus 1 times B. And all you do is just simply plug in. And so AN would be 36,800 plus 1750 in. Okay, that would be the formula for your salary in years. And part 2 says determine the total amount of money made during 6 years of employment. Okay, so we're looking for S6. So S6 is something over 2 times something plus something minus 1 times something. Okay, so plug in 6. A1 is 36,800. This is 6. Common difference is 1750. Okay. So you would have made 247,050. So over 6 years, you made $247,050. Okay. So again, these are some of the applications you can see for arithmetic sequences. You want to find the total amount of something. Right. So now we're going to get to the last part of our lesson, which is developing a formula for a sum of a geometric sequence. And it says, consider the geometric sequence A1, A1R, A1R squared, all the way up to A1R to the K minus 1 power. It says, write the expanded form of this series from K equals 1 to N. Okay, so that would be term 1, that's A1 plus A1R plus A1R squared plus A1R cubed up to AR n minus 1 A1R to the N. Okay, that's the expanded form. Second, excuse me, write the expanded form of this series. A1 times R to the K. So we have A1R plus A1R squared plus A1R cubed, dot, A1R to the N minus 1, A1R to the N. Okay. And so now we have that. So now it says let SK minus 1 equal the following series. Okay. Find an expression for SK. All right. So let me do this here. So SK minus 1. Okay, so you got the blue expression. A1 plus A1R plus A1R squared, A1R cubed, plus A1R to the N minus 1. Plus A1R to the N. And then we're going to add to that A1R plus A1R squared plus A1R cubed plus A1R to the N minus 1 plus A1R to the N. Okay, so now what's going to happen is you're going to have some cancellation. So that's supposed to be plus sign here. I'm sorry, a negative sign, excuse me. Negative sign. So we're going to have cancellations here, there, including that. And then all of these terms also canceled out. Okay. All right. And I think I made a typo here. And I look back at it. This is supposed to be N minus 2 and then N minus 1. So this will be N minus 2, N minus 1. Excuse me. That's supposed to cancel out. So we have A1 and A1R to the. Okay, so let me kind of move this up so you can see. Let me move this up a little bit more so you can see. I'm about to write here. Okay, so now here's the thing. That this right here is the second sequence. And really what we did was, if you look carefully, we actually took this series and multiplied by this blue series multiplied by R to get the purple. So this SK minus 1 is actually going to be R times SK. And then that's going to leave A1 minus A1 R to the N. Okay. A1 R to the N. And so on this side, you want to factor out the R. So that's going to be R times 1 minus, I'm sorry, not R, SK. Factor out the SK term, excuse me. 1 minus R. And then you have A1 minus A1R to the N. And then you divide both sides by 1 minus r. So let me shrink this. You can still see it. Okay. And so when it's all said and done, we have SK equals A1. So up here you can factor out at A1, at least 1 minus r to the n over 1 minus r. Okay. And that's the expression for SK. So what we've just done is we actually derived a formula that allows us to find the sum of a geometric sequence. Okay. And that's what that leads to, a sum of a geometric series. Okay, so we have two types of geometric series. We have a finite geometric series, okay, that goes from 1 to a certain number, okay? And then for the sum, it's A1 times 1 minus r to the n over 1 minus r, okay? Or you can just keep it like we had originally, where you keep the A1 in there if you want to distribute it in there. So either formula works. Then we have another type of geometric series called infinite geometric series, where you just keep adding things. Okay, you keep adding terms over a period of time. Okay, but this series, pay attention to the fact it starts at 0. Okay, so from n equals 0 to infinity, we have AR to the n, and here's the formula to find its sum. So A over 1 minus r is the sum of the infinite geometric series, where the absolute value of r is greater than 1. So this is actually going to be very important for those of you that are actually going to calculus BC. Sequences and series is actually a topic that is very intensely visited. So there are some prerequisite skills you definitely want to know before you get exposed to sequences and series in calculus. This is the sum of an infinite series, infinite geometric series. Okay, so now let's start working with some problems involving finding sum. Okay, we want the sum of the first 7 terms of this geometric series here. And how do I already know it's geometric? Well, each time I'm multiplying by 3. So it's times 3, times 3, times 3, right? Okay, sum of the first 7 terms. Okay, so that's S7. Okay, so we need the first term, so 10 times 1 minus r, so that's 3 to the power of 7 over 1 minus 3, okay? And if you want to simplify that, you can. What's going to happen is you're more than likely going to get a decimal here. You really want to know what the actual number is, because these things, the thing about these sums for geometric series, they get out of hand quick, fast, in a hurry, as you can see here. Okay, so this one gives you a sum of 10,930. 10,930. Okay, that's the sum. 10,930. And so again, let me remind you here that A1 is 10. This has a common ratio, R, not D, R. D is for arithmetic, R is for geometric. Okay, so A1 is 10, R is 3. All right, now we're going to find the sum of this finite geometric series, n equals 1 to 12, 16, 1/2, n minus 1. So you will need definitely the first term. So the first term, if you plug 1 in, you get 16. Of course, r is 1/2. It's that number right there. So we need the sum of, looks like 1 to 12. That's 12 terms, so S12, okay? That's going to be 16 times 1 minus 1/2 to the power of 12 all over 1 minus 1/2. Again, like, as you can see, these get very, very messy, especially when we start bringing in fractions. Okay. So I get I'm actually going to write it as decimals here. Correct to 3 decimal places, 31.750. Okay, 31.750. Correct to 3 decimal places. So you're going to find the sum of a geometric series. Round your answers correct to 3 decimal places. All right, now here's an interesting one. This time, this one goes to infinity. So we can't use the formulas we used before. We have to use the one I showed you earlier for infinite geometric series. Okay, so you want to definitely check and make sure your ratio is, when you take the absolute value of it, is less than 1, and it is. So here we have A equals 4 and R equals 1/2. But because of the infinity, okay, we have to use another formula. So S, call it S infinity. That's A over 1 minus R. Okay, A over 1 minus R. So here S infinity equals 4 over 1 minus 1/2. And you get S infinity equals, that's going to be 8, I believe. I always want to double check and make sure. 8, yes. Yeah, 8. All right. If you understand those problems, here's some practice problems for you to do involving finding the sum. Okay, finding a sum. So remember, pay attention to when your top bound is either a number or infinite. That's going to help you determine which one to use. All right, so now we get to some applications. Why geometric sequences and series? Well, most of you love money, so there's a problem dealing with compound interest. Okay, so Linda wants to invest $20,000 in a savings account that pays 3.4% annual interest compounded monthly. We're asked to do 2 things. We're asked to first determine a formula for the amount of money in the savings account after n years, and then 2, determine the amount Linda will have in her savings account after 10 years. Okay, so let's go back and review this again. It says Linda wants to invest $20,000 in savings. So that's our A1. This is, okay, our R, 3.4% annual interest compounded monthly. So that's going to actually make a difference here. When you see compounded monthly, that means we get interest 12 times a year. Okay, so I'm going to call that, call it K here. So K is 12. So we get interest 12 times a year. Okay, so they're going to divide this up into over 12 months. Okay, so you should have remembered that from a unit back in Algebra 2 regarding exponential growth and decay involving compound interest. All right, this says determine a formula for the amount of money in the savings account after n years. Okay, after n years. So that's a geometric sequence. Okay, because what's happening, okay, this is what's happening. Take an original amount, right? And then I take a percentage of that and add it back to the original balance. And then I have a new balance for the next month. And then that process repeats over and over again. Okay. So AN is going to be let's write our formula first for the geometric sequence. Okay, so it's AN equals A1 times R to the N minus 1. So in this case, AN is $20,000. 20,000. Okay. Now we got to be careful here. Okay. 1 plus. Okay. We got 1 plus 0.034, 12 to the power of N minus 1. Okay. And I would probably leave it like that. Okay. Now it says determine the amount Linda will have in her savings account after 10 years. Okay, so that's will be the sum of the first 10 terms. Okay, so we're looking for S10. So S10, we got 20,000. 1 minus, we got to deal with that. Let me see what that is. So this is going to be 1.002833333 repeating. Over 1 minus 1.002833333. Okay, so let's put that in calculator, see what she's going to have. Okay. So it says after 10 years, you should have over $200,000. A lot of money. A lot of money. So let's think about this carefully. After 10 years, okay, she's gonna have that amount of money in 10 years if she saves up that amount of money. Okay. But we have to be careful. It says determine the amount Linda would have in her savings account after 10 years. And it says how much she gets over 10 years. Okay. So you're looking for A10. That's what you're looking for. Okay. So here you're looking for term number 10. E to the power of 9. Actually, no, I take that back. Sorry. This would be term number 11. Term number 11 is the 10th year. Okay. My apologies on that. Okay. So she will have 20,000 573.94653. So after 10 years, you will have $20,573.95 after 10 years. So she would have gained an additional $573.95 after 10 years. Okay. Now the amount that I used before, that's how much money she would have accumulated over 10 years. How much money would she have accumulated over 10 years? So that's what the sum does. The sum is going to accumulate the amount of money she has over 10 years. This is saying how much money is she going to have in the account in the 10th year. We got to make sure we understand that. Okay. All right. So last real world example deals with, of course, uh, bacteria, viruses, and stuff like that. And so um, for those of y'all going into the sciences, it's good to know, um, how quickly bacteria multiply. Okay, and it says the number of bacteria in a culture is increasing by the law of exponential growth. After 3 hours, there are 100 bacteria. After 5 hours, there are 400 bacteria. And we're asked to determine a formula for the number of bacteria after n hours. And then part 2 says determine how many bacteria there will be in the culture after 12 hours. Okay, so let's go back in and read this again. Exponential growth. Exponential growth is going to imply we have a geometric series, a geometric sequence. Okay, after 3 hours, there are 100 bacteria. So that means A3 is 100. After 5 hours, 400 bacteria. So A5 is 400. Okay. So it says determine the formula for the number of bacteria after n hours. So we don't know R and we don't know the first term, right? So we're going to have to do some work to obtain R, the first term. Okay. So this is what I know. Okay. So to get from A3 to A5, I have to multiply R 2 times, right? I have to multiply R 2 times. Okay. So what I'm going to do is take A5, right, divided by A3, and that's going to equal R squared. So in this case, I got 400 over 100 equals R squared. So 4 equals R squared. That implies that 2 equals R. So our common ratio is 2. Okay. Okay. Common ratio is 2. So now I can use this to find my first term. So based on this, if after 3 hours, I have 100 bacteria, then actually the first hour, the first term would be, so the first term would be 100 divided by 2 times 2, because 2 hours elapsed since 3 hours. So that's going to give you 25. So we know that A1 is 25, and we can go ahead and write our geometric sequence. So AN equals A1 times R to the n minus 1. And that gives us a formula of AN equals 25 times 4 to the n minus 1. Okay? 25 times 4 to the n minus 1. And then part 2 says, determine how many bacteria will be in the culture after 12 hours. Okay, so we're looking for A12. So A12 is 25 times 4 to the 12 minus 1 power. So after 12 hours, a lot of bacteria. Okay, that's a lot of bacteria. Okay, so this is how much bacteria will be in the culture after 12 hours. After 12 hours, okay? That much. So, yeah, about 104 million bacteria. That's a lot of bacteria. Okay. And this concludes the video on series. Thank you so much, and hope you enjoy the rest of your day.